Hello everybody watching this video. This is Professor Altania here. I'm not really a professor, but I thought about making this video anyway. I've recently been thinking about how arrays work, and realized that Minecraft would be a pretty good medium to kind of show that, in a visual sort of way. So today's video I'm going to be talking about how arrays work, how array list and list works, as they're called in C#. Other languages may call them other things. I believe C++ calls them vectors. How linked lists work, and in C#, linked lists are doubly linked, whereas in some other languages you can have doubly linked and singly linked lists, but they follow the same logic. And how the binary search algorithm works, which is really brilliant. I love it a lot. So, without further ado, let's get to it. Alright, I'm over here in a fake piece of memory. I have numbers 0 through F, which, for those of you who do not know, is 16 possibilities. 0 through 9 is 10 possibilities, and A through F is 6 possibilities, and so 16 possibilities total. And the same thing over here. When I work out coordinates, I'll be referring to this first and then this. So let's start with arrays. And also let's start with the color coding. Blue is data that I'm interested in. Red is data that I am not interested in. This gray is just used for the floor. Yellow is data I have, space I have available to me that's been allocated specifically for me but does not contain any meaningful data yet. Black I just use as the background. Green and pink we'll get into later. But let's go ahead and start with arrays. So, what is an array? An array is just a collection of something. In 32-bit systems, integers are 4 bytes. Each block here is going to represent 1 byte, by the way. So this would be an integer, 4 bytes long. Okay. If I had an array of integers 2 integers big, I would have 1, 2, 3, 4 bytes for integer number 1, 2, 2, 3, 4 bytes for integer number 2. The entire array would take up 8 bytes, or 2 integers worth of data. Similarly, if I had an array of 3 integers, it would be 12 bytes, 4 for each. 1, 2, 3, 4, 2, 2, 3, 4, 3, 2, 3, 4. Okay, so let's go ahead and go back to that 1, 2, 3, 4, 2, 2, 3, 4, 2 integers. This is my array. I have told the computer, please give me an array of 2 integers, and this is what it gave me. It says, here's the beginning of the array right here. And it's 2 integers. I know an integer is 4 bytes in this case, so I know that this array is 8 bytes total. So all I have to do is start at the memory address right here, which in this example is 0, 1, and just count 8 bytes to get my entire array. If I want to get the first element, I know that's just 0, 1. If I want to get the second element, I know it's 0, 1 plus 4, which would be right here, 4, 5, 6, and 7. Along this row or column, I suppose it depends upon how you're oriented. By the way, another thing to note is I made this a square. You could have a representation of it just going all the way straight, but I just thought this was more compact. Okay, so why is it that whenever you declare an array like this, you can't just grow? Because look, I mean, we have room. Couldn't I just say, hey computer, I know I told you I needed 2 integers worth of information, but actually, can you make that 3? And it would say, sure, 1, 2, 3, 4. And I can't do that because sometimes it could just so happen that another variable in my program takes up some information right there. Well, that's going to cause a problem. Or maybe it's not from my program. Maybe it's from some other program running on the computer. Or maybe it's not right there. Maybe it's right here. And suddenly I can't do this. This is going to be a problem growing the array if you cannot always be guaranteed you're going to have the space. Sometimes you might. Sometimes there may be, hold on a second. It's raining on my parade. Sometimes it could very well be that you have enough space to add on another integer or 2 integers or however much you wanted to grow your array, but it can't guarantee that will always happen, and so it just doesn't let you do it in the first place. So that's what an array is. It is a collection of a certain type, and if you know the size ahead of time, you can make it as big as you need to. It'll find space, it'll move things around, but once it is set You can't really make it grow. You cannot really change it. And of course, it would kind of be teasing to allow you to shrink it, but not allow you to grow it back. So you just don't have the functionality to do either. You set it, and that's that. But that's not really flexible, is it? Because what if you wanted to grow the array? You do have instances where you have a list of students and you need to make more room for students because you had a couple new enrollees. Well, introducing the concept of array list, or list as they're known in C#, here's what the computer does. I have 2 integers and I want 3 integers. So here's what one of those array lists is going to do. It's going to find some other part of memory. Let me go ahead and put this back here just to kind of exemplify that I can't grow that any further. There's something in the way. There may be something in the way. Maybe there won't be. Maybe there will be. So here's what the computer does. It says, okay, let me first of all create another array. You say you need space for 3 integers, so I'll make space for 3 integers. 1, 2, 3, 4. 2, 2, 3, 4. 3, 2, 3, 4. And it says, okay, let me come over here and let me copy the data from this array over here. That's 1 integer. That's 2 integers. Okay, now I can delete this array. I no longer need it, because now all the information's been copied over here. And now, go ahead and replace this last integer with whatever data you want. Okay, I've just now grown the array. It found another space, and it didn't really grow it. It just made a bigger one and copied everything over. It's kind of like moving into a big house. Okay, that's pretty cool, except sometimes this will happen. Hey computer, I want another array. This time I want to store one more integer. 4 integers total. Okay, Altania, I can do that. 1, 2, 3, 4. 2, 2, 3, 4. 3, 2, 3, 4. 4, 2, 3, 4. But it's not done yet. 5, 2, 3, 4. 6, 2, 3, 4. 7, 2, 3, 4. 8, 2, 3, 4. What? Okay, Altania, I'm going to copy over your data now. 1 integer, 2 integers, 3 integers. Okay, Altania, and now the data you told me to put into this new element is going right here. There you go. Hey computer, I no longer need this array. This entire thing, these 8 integers worth of spaces, I forgot one, sorry. These 8 integers worth of spaces is now my array I'm working with, which is twice as big as I needed it to be. Why is that? Going back to the whole student example, let's say that you had a program that was supposed to manage a few thousand college students, and you wanted to enroll somebody. So imagine that this array was super huge, bigger than this entire thing you see right here. Does the computer really want to have to declare another array that's even bigger and copy everything over from one array over to the other every single time you add a student? It does not. So, when your array starts getting big enough, it starts declaring more space than what you told it. It's kind of thinking ahead, if you will. It's planning, okay, if he wants to add another integer, I don't have to copy everything over to another array because I made extra room for myself. Hey, computer, I want a 5th integer now. 1, 2, 3, 4. There you go, Altania. No copying needed. Hey, computer, I want another integer. 1, 2, 3, 4. 1, 2, 3, 4. There you go, Altania. No copying needed. But this does introduce 2 properties to this array. First of all, this array is of a certain size. It is 8 integers big. However, I'm only using 6. I don't know exactly what it's called in other languages, but in C#, the size of the array, how much you have access to, is how much you told it you have access to. The actual size of the array is how much it is allocated for future use. Okay? So if I say I want to get integer element 0, remember, things in programming are base 0. This is this first one right here, the second one, the third one, the fourth one. the fifth one, or the sixth one. But if I try to say, please get array element number 7, which is the very last one right here, it throws an argument out of bounds exception. Why? Because I only told it I'm using these 6 integers, not 8. But it has room for it. Yes, it does have room for it. But this data is trash data. It's meaningless data. It allocated it, but it didn't initialize it to anything because we're not using it yet. It would have to initialize every single time regardless, and it's possible we're not going to use this, so why waste time initializing it when we may not actually use it, when it can initialize it whenever it needs to. So this data technically is allocated to us, but it's trash data. It doesn't mean anything, and if we try to access it, we're going to get some unexpected data that we don't know what to do with. It wouldn't be meaningful to us. So it only lets us go up to how much we told it we need, even though technically we have more than that. In C#, this variable right here is called count. This variable right here is called capacity. And according to the C# source code that Microsoft has made open, their lists like this, by default, start off for of whatever data type you're working with big. And whenever it reaches full capacity, it doubles in size whenever it needs to go beyond it. So if I filled up this all with integers and I wanted to go beyond it, it would then give me, instead of 8 integers, 16, even though I said I only want one more. And then if I filled all that up and I wanted one more, it would allocate 32. So it keeps doubling the size, starting with 4 of whatever data type you're working with. So just be careful. You want to use count, not capacity. Capacity is the total of everything that it can possibly have. Count is how much you're actually using. I think that kind of makes a little bit of sense based upon how the words are used in English, but that's just me. If you want to think about it, though, think about the word count is smaller than the word capacity. Capacity has 4 syllables, count has 1, count has 5 letters, capacity has 8, I think. COUNT, yes, it does. So you can think of it that the count will always be less than or equal to capacity. Capacity will always be greater than, or it'll usually be greater than, count. If that helps you think of it, awesome. Okay, there is another way we can store this data, though. That's even more flexible than this, although it takes up a bit more space, and that in C# is called linked list. We'll get to that next. I gotta clean this up first, though. Alright, I'm outside of my fake memory right here just to kind of show how this data structure looks. This is called a node in a linked list. It consists of 2 pointers and the actual data. Right here I'm using 2 bytes of data, so short data type, or use short if you want. You notice I have labels here back and forward. Pointers are nothing special. They just store a coordinate that says this is a particular place in physical memory that I am referring to. It refers to things by reference. It gives the address. It does not actually store the data, just the address to where that data is located. This back will always refer to the node behind it. Always when I'm trying to record, I tell you. This back refers to the data that should be behind it in a list, and this forward should point to the data ahead of it in a list. This is the actual data itself. Again, for this example, I'll just be using 2 bytes. So, let's clean this up. Okay, so let's start off with our first node. By the way, the reason I'm using 4 bytes to reference a pointer is because on 32-bit systems, 4 bytes is in fact the size of the pointer. It takes 4 bytes to represent all possibilities of data. On a 64-bit system, it takes 8 bytes, I believe. So here is our first node. Since this is the first element in the list, there is nothing behind it, so we are going to say reference null. It points to nothing. Currently, this is also the last item in our list, so this also references null. I only have 2 bytes and I spent 10 bytes representing it. Why is this any good? because here's some data that's blocking the way of having a continuing list. And I say I want to increase my list. I want to add another element. The computer says, no problem, no problem. 1, 2, 3, 4. 1, 2, 1, 2, 3, 4. I found space for you, for your second element. But remember, the whole thing with the array is that we could just start at a beginning and just walk a certain distance based upon how big the data type was we were using and which one we wanted to get. Simple math, right? Well, we can't do that if all the parts are disparate, so we have to somehow link them together. This is where the whole memory address thing comes into play. So I always remember where my first one is. I never forget that. I don't know where my second one is, or I do now because I'm in the middle of creating it, but once I get done creating it, I'll forget where it is directly. So I want to somehow link those two up. So what's this memory address? This starts at 3, 4. So I'm going to come over here to the element before it, which in this case happens to be my first one, but may not always be. And I'm going to say reference 3, 4. Okay, so if I want to go forward, I can reference 3, 4. Similarly, if I want to go backward, I want to reference this, which is at 0, 1. Okay. So, reference 0, 1. Well, that's cool. So I start off at null, and if I want to get to the second element, all I have to do is say, okay, I know each pointer is 4 bytes. I know the data type in this particular collection of items is 2 bytes. So what's that? 1, 2, 3, 4 for the first pointer storage, 1, 2 for the data, 1, 2, 3, 4. I am at my second pointer. I say, hey, pointer that points forward from the 0th element. What is the address of the element number 1, the first element, which is actually the second element? It says 3, 4. So I say, okay, I'm going to go to memory address 1, 2, 3, 1, 2, 3, 4, right there. Okay. So, oh, I'm here. I want to access the data in this element, and I know that it starts with a pointer, so I have to go 1, 2, 3, 4, and then these next 2 bytes will be my data. So I can still do math, but I'm simply storing the address of the next one. Okay. This, by the way, is reference null, because this is at the end of the list. And if I ever see a reference of null, I know it's at the end of the list. Okay, so that's cool, that's cool, that's cool. I want to have another one. Computer, please give me another one. Okay, it says 1, 2, 3, 4. 1, 2. 1, 2, 3, 4. I do the same thing. I'm currently holding on to this because I'm in the middle of creating it. And I go to the beginning of my list. I find reference 3, 4. Okay. And I come here and I say, oh, you're null. So you're currently at the end of the list? Okay, well, you're the one I want to link up to then. I make a note of this. It is at 3, 4. I come over here, which I'm remembering, and I'm saying, hey, you need now to reference backwards to 3, 4. Since you're at the end of the list, by the way, reference null because you're not going to be pointing anywhere. You're at the end of the list. And I come back here and I say, okay, you are at 0D, as in delta. Okay, so I'm coming over here and I say, okay, now you're going to reference 0D. So now let's just make sure this works. I always know where my first one is. And I go and I say reference 3, 4. Okay, this one is 3, 4. If I want to go backwards, I can reference 0, 1, which is right there. Otherwise, if I want to go forwards, I have to reference 0D. This is 0. This is 4, 5, 6, 7, 8, 9, A, B, C, D, right here. Okay. And if I want to go backwards, it references 3, 4, which is right here. But if I want to go forwards, I can't. It's null. Okay, that works. I can traverse this list forward and backwards. Computer, I want another one. Let's just do another one. Let's put it right here. Okay, Alternate says I can do that. 1, 2, 3, 4. 1, 2. 1, 2. Oops, forgot this one. 3, 4. So this is the reason I did it this way is just to show you that this data, this representation, it's all just one line. I'm just kind of condensing it into a square so it's easier for me to go back and forth on. But this is all one thing. I just hope you see this. It's like it's wrapping around to the next one in this example. Okay. Well, They also don't have to be in order memory-wise. This one's kind of in the middle here, even though it's going to be at the end of the list. Alright, so this is the end. I know that you are reference null because you are at the end of the list. I just created you, so I'm still remembering that you are at alpha 6. Okay, so you no longer reference null. You reference alpha 6. Awesome. Also, you need to point back here, which is at 0 delta. Okay, reference 0 delta. So now I can go forward to alpha 6, I can go backward to 0 delta. And if I am at alpha 6 here, and I continue on the list, which continues on over here, I'm at the end of my list here, null. I go backwards to 0 delta, which is right here. I want to go backwards to 3, 4, which is right here. And I want to go backwards to 0, 1, which is right here. Okay, so that works. That works. What if I wanted to insert something into the list? This right now is my last element. This is my next to last. I want to add something before this. Computer, please give me another. Okay. 1, 2, 3, 4. 1, 2. 1, 2, 3, 4. I'll make this easier again. Okay. So, I want this one to reference back to this, and this to reference back to whatever this was. Let's see. This was referencing 3, 4, which is right here. So instead, I want this to reference 3, 4. Okay? And this is at what? This is at 4, 9er. Okay, so instead of referencing back 3, 4, you're now going to reference... What did I just say? Did I say it was 4? Hold on a second. I already forgot. Yeah, 4, 9er. Okay, so you're going to reference 4, 9er. So if I go back, I'm here. If I go back again, I'm here. Okay, now you need to reference 0 delta going forward. So, reference 0 delta. You're now pointing forward to here. You're still pointing to alpha 6, which is right here, and you are still pointing next to nothing. So, I can go here, which then takes me to 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 here. It looks confusing. It is. It can be haphazard, but that's how flexible it is. The computer can put it anywhere in memory. So long as it remembers what's pointing to what, forward and backward, it can put this stuff anywhere in memory. No problemo. So it looks confusing to a human, but a computer, it's got this down. So long as you understand the process of what's happening here. I do want to show deleting. I'm going to delete this one. Should I delete this one? It is the last one in sequence. I do not want to do that. I want to delete this one. Okay, we'll delete this one. Hold on a sec. Sorry, I had to cut my recording there a bit. Okay, so we wanted to delete this element. Before we did that, though, we needed to link up what's before it to what's after it. Okay, so 0, 1 is the one before it. It might not always be the first element in our list, but in this example it is. So I know which one I want to delete. I look at, okay, you're 0, 1, so I go to 0, 1. I say, okay. Yep, you are in fact the one before it. What's the one after you? 4, 9? Where's 4, 9? 4, 9er is right here. I say, okay, the one before it is going to have to reference the one after it and vice versa. So I currently have in memory the location of the one I want to delete, the location of the one before it, and the location of the one after it. So I say your 49er. The one before it, you're now going to point to 49er as your next element. 49er, as your previous one, you're now going to point to the one before the one I want to delete, which is right here. So right now, my reference 01 should match this reference 01, and this reference 49 should match this reference 49. Good. I just now tied together the ones on either side of it. Boom. A lot less complicated deleting than it is building up, which is a metaphor for life, by the way. Things are much easier to destroy than to construct. Okay, so let's go. Reference 49. We're at a first element. Reference 49. Reference 49, 49, 49. Here you are. Reference 49er. Okay. Reference 0 delta. Here you are, 0 delta. Reference alpha 6. Here you are, alpha 6. Follow you all the way because you're up around. Reference null. We're at the end. Let's go backwards. Reference 0 delta. Reference 49er. Reference 0 1. So yeah, I can go back and forth on this list, and I can add elements in between and at the end, and the same logic happens for the beginning, and I can delete items in between or at the end, and the same logic goes for the beginning. This takes up a lot of space. As you can see, this takes up 2 bytes for a short data type and 4 bytes each for a pointer on a 32-bit system. If I have an object which is a student, it'll be 4 bytes because objects are referenced by their memory location. The entire object is not stored because that can be a huge thing, and if you want to pass it as an argument, it would be a lot of work passing all that data in through an argument through a method. So instead it just references the object, just sends a pointer, because a pointer is no bigger than 4 bytes on a 32-bit system. But still, best case scenario, or worst case scenario I should say, well, I suppose you could always do a lon that's 8 bytes. But usually you're working with integers or objects, and so you're left with 4 bytes for the back pointer, 4 bytes for the data, and 4 bytes for the next pointer. That's 3 times as much storage space as needed if you just had a simple array, but it lets you add on and remove things in the middle or the end at a guaranteed, well, kind of guaranteed. The actual act of removing and adding is of a set speed. You don't have to copy more and more data over as you did with a list. But it does take up more space. Also, iterating through them is slower because you have to go to every single one and look up the next one and look up the next one and look up the next one, etc. Whereas if you had things stored in a sequential order, you can just skip over the amount you want to skip over times the size of the data. It's really simple math, allows you to just zip on through and get to the right element. So iterating through a linked list like this is slower. It takes up more space, but when it comes to adding and when it comes to removing data, it is a lot more flexible. Okay, so let's have some fun and talk about the binary search algorithm. Now, it's a little bit difficult for me to demonstrate the actual binary search tree, but the binary search tree is just a specialized form of a linked list that uses the same logic, but it's the algorithm, the logic, which to me is really cool. So I have already set up a number of signs, 40 of them actually, that each contain a different number in increasing order. A binary search algorithm only works if the list you're giving it is sorted in some way. And I believe the default algorithm looks for it to be sorted from least to greatest, but if you flip the algorithm the other way around, you could have a list the other way around, doesn't matter. I included these marks right here, that's just for my own benefit, to help me count, to help me keep track of which one I'm at. So, binary search algorithm is easy-ish. Let me go ahead and pick a number from the list, let's say 54. But let's pretend I don't know exactly where that is. I could go through, and I could say Element number one. No, not 54. 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 54. Found it. Not 54. And it's the only one. I could do that. If it was the last number on that list, that would have taken a while. Let's try to find it in another way. So like I said, I have 40. I broke this up into sets of 4. So 4, 8, 12, 16, 20. 24, 6, 4, 8, 12, 16. Yep. Okay, so here is the middle. And here's where I'm going to be using the pink, just to kind of say, I've now split the list into two sets of 20. Now, since this is an even numbered list, I can't look at exactly the middle, but I'm gonna say, let's look at this one. 99. I know everything's sorted, right? So I know that everything to the right of 99 is greater than 99, and everything to the left of 99 is less than 99, or possibly equal to. Okay. So, I'm looking for 54. Is 54 greater than 99, or is it less than 99? It's less than 99. Since everything to the right is greater than 99, I know immediately it can't be any of those. What have I effectively done? I have effectively chopped down my list of 40 to 20 by looking in one place. Okay, let's work with this half then. So now I'm down to 20, so now I want to split it in half again. 4, 8, 9, 10. So that should be here and here. Okay. I'm going to look here again. 53. Are you less than or greater than the number I'm looking for, 54? Because I know you're not. Oh, you're less than 54. Okay, so I know immediately it can't be any of these. Okay, so now I'm in between here. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. Ooh, now I have an odd number. I can split it up evenly. 1, 2, 3, 4, 5. This is where I'm at now. 77. You're greater than 54. Okay. So I can discard you guys. Now I'm just left with 1, 2, 3, 4, 5 possibilities. 60. You're greater than 54. So I know you're not it. You're one of these three. 55. You're greater than 54. That leaves me with only one possibility, 54. Now, yes, I know when I was looking here at 53, 54 is right there, and you're probably screaming at your monitors, it's right there, just look to your right. Well, the computer's not that smart. But it chops the list in half each time, which, if you have a lot of students, so long as they're sorted, can help looking through them easier. I believe if you have 100 elements to look through, it takes you at most 7 lookups to find the one you're looking for. Whereas if you just went through it iteratively one at a time, at worst case scenario, it'd take you 100. But in a binary search algorithm, again, assuming everything's sorted, least to greatest, with 100 elements, it takes you at worst 7 lookups, not 100. So you can see why that may be faster. Now, you may have also noticed that running through here, I had two 40s. You may or may not be working with a type of data structure that wants you to use repeating values. It could be that you have to work with things that have to be unique, and so you'll never run across this situation. I believe the rule is that values that are the same are placed to the left-hand side. So for instance, if I was in the process of adding these numbers here, and I'm not going to do that just because, again, it's really difficult to move blocks around in kind of a tree form and to make them bigger in Minecraft. It's wonderful for that, but not so much here. But if I was to do that, and I did not have this 40 and I wanted to add a 40, what I would do is if I saw when I was going through my tree, because when I'm adding, I do the same thing. I say, I want to add this number. Let me try to find it first. And then whenever I get to the end of the list and I have one possibility left, like let's say I wanted to add, let's say actually I wanted to add 52. No. Now let's make it 50, just to put it here. So I went through the list, I went through that thing, and kept on chopping it in half till I got to 52, and then I said, okay, I want to add 50. So right now I'm here. I finally found 52, and there is nothing to the left or right of it that I've not already ruled out. Is 50, the number I want to add, less than, equal to, or greater than 52? It is less than. So I put it there. 50. There I go. And by doing that, by doing the whole split in half until you find the one you're looking for, and then following the same type of logic, less than you go to the left, greater than you go to the right, and I just put it there instead of look there now because there is nothing there, so I add it there. I have put it in order. It following the same logic to put things in places rather than just looking them up also sorts them. Okay, that's cool. Let's say I did the same thing this time with 55, except I want to add another 55. I get to 55. I say 55. Are you less than or equal to or greater than 55? You are equal to 55. I have two 55s here. Assuming that's okay for the type of program I'm writing, I add it to the left. That's all. I could have added it to the right too, but just to be consistent, you always want to do the same thing. So, what does that mean when I'm looking up data? Let's go ahead and look up data again using the binary search algorithm, except this time I'm going to look for 40 because there are two 40s. So first of all, I'm going to split the list in half. 4, 8, 12, 16, 20. Okay. I'll look in here again. Actually, for the purposes of this, yeah, let's go ahead and look here. 99, okay. 40, you are less than 99. I can eliminate 20 of them already. Okay. So, 4, 8, 9, 10. 40, you're less than 53. Okay. Thank you, rain. Okay, so, yeah, it always rains all the time. I say that, but it usually doesn't. It's just when it does, it kind of stands out. So, I eliminated 40 down to 40 possibilities down to 20 possibilities, and I do realize I picked the number 40 for my example, which is confusing because there are 40 elements total. Just ignore that. I'm talking about two different things. So down to 20, down to 10. Okay. 1, 2, 3, 4, 5. 6, 7, 8, 9, 10. Okay, so I did split it in half again. Oh, you're greater than 21, 40. Okay, so now I'm working with this set. 1, 2, 3. 40, you're less than 44. So now I'm dealing with these 3. Technically 2, really, but okay. So let's look here. These two I've not considered. I am looking for 40. I found 40. I have not found the only 40. So it's kind of crucial to say, am I going to return the first thing I see that happens to match this, or am I going to continue looking for anything else that happens to match this and return a list of all 40s? Because if I wanted to do that, I know that anything equal to this is going to be to the left. So if I found what I'm looking for, what I can do is I can say, okay, I found what I'm looking for. Let me just look to the left one spot and see if it's the same thing. And if it is, let me look to the left one more spot and see if it is. But in this case, it's not. So I can look up two 40s, or I can just return the first one I found. Doesn't matter. It's still in order from least to greatest. And if you iterated through them one at a time, you'd be left with the same problem. Once you find it, what's to say that the next one's not the same thing? So you still have to worry about the same thing, about finding duplicate data and how you're going to handle that. But just know that duplicate data is traditionally always kept to the left. Whenever you store it, you put any data that's less than or equal to something that you're looking at to the left, and data that's greater than you store to the right. So that's how the binary search algorithm works. Like I said, it's pretty simple logic, really. You just keep on splitting your list in half by looking at the middle and saying, are you too big or are you too small? Because if you're too big, everything to the right, you use too big too. If you're too small, everything to the left, you use too small too. And I can just chop my list in half. 100 after one lookup becomes 50, after another one becomes 25, then either 12 or 13, and then assuming worst case scenario is 13, either 6 or 7, worst case scenario is 7, either 4 or 3, worst case it was 4, then it becomes 2, then it becomes 1. You found it. Okay, 7. I think that was 7 lookups. So binary search algorithms, brilliant at doing this kind of thing. but again, it has to be sorted. The binary search algorithm will technically work if the list is not sorted. It'll still run, it'll still give you an answer, but it may not be what you were expecting. It'll be a logical error. So do make sure the list is sorted before you do that. A binary search tree, you may find this in your library, is basically just a fancy linked list, except instead of adding things to the end of the list, whenever you want to add a number, it iterates through it. It remembers the first value, which is actually the middle, and it follows the same logic that I did when trying to add a number like 50, and it goes through the list. It looks at the first element, it says, are you bigger or greater, then goes to the next one, etc., etc. So each element in the linked list is actually linked to the middle, quote unquote, the middle of the sub half. And so it forms a kind of tree. It looks something like this. I'm just doing this because of space constraints. It looks something like this. So this is the first element, the one I always remember, and then to the left is this, to the right is this, and then to the left is this, to the right is this. So ordinarily, like you would have, if this points to the right here, then this to the left will point back up. Instead, you have the left pointing somewhere else. Some binary search trees actually have 3 pointers, one that points back to parent, one that points to left, one that points to right. You can do that definitely, but all you really need is just to point to left and right, and just know that in this structure, the left and right pointers do not point forward and backward along a list. They point to the next one below them. They do not point back upwards. So if you iterate down through a list by following a bunch of lefts, and you go to the right, you will not go back to where you started. But it is still the same thing where you just have pointers pointing to other places in memory, so each of these nodes can really be all over the place and they just point to each other. It still follows the same logic. Get to the first one, go to the left if you're too small, go to the right if you're too big, etc. until you run to one where you has no children in the direction you need to go, and you know that it goes in that direction. So same logic, just a fancy implementation of the linked list, but really the algorithm itself works with any sorted list. So you can use it with an array, or with an array list, or with a list, or with a linked list. Anyway, I hope that helps. I know that seeing it visually, for me, helped me kind of see how things were laid out and things like that and where they're all connected and kind of walk through it. Because not very often in computer code do we actually get a walk through, literally walk through the code. And being able to do this in Minecraft, to me, seemed like, duh, of course you do it here. Hope you enjoyed. Hope you didn't become all too confused. Yeah. I have no clue if I'll be doing any more videos like this to explain concepts. I can't really think of too many other programming concepts that kind of go really well with a sandbox game like Minecraft. Maybe there are some, maybe they're not. But I know that explaining how memory management works to me seemed like obvious choice. Actually, originally Legos seemed like a good choice, but then you know what? Minecraft is so much easier than Legos because they're not plastic and they don't hurt your hands each time you try to take them off. I love Legos, by the way. Okay, enough rambling. Thank you for watching. Goodbye.